Welcome to this next lecture on acoustics. We were looking at the acoustic wave equation and its separable solution in spherical coordinates, and we were working on method of separation variables, and this is where we were last time. So we have separated the r and the theta phi, okay, so that now we say, so this has to be another constant, right? This has to be another constant, So what we say is 1 over r d by dr r square dr by dr plus k square r square, okay, is equal to n into n plus 1. Okay. Now why n into n plus 1? Okay, because this equation here, okay, has continuous solutions. In the range cos theta is equal to minus 1 to cos theta is equal to 1, okay, only if n is an integer, let's see, integer. Okay, so it's a little more advanced for this level, so I will leave it at this. If you want more details, then they are there in this foundations of acoustics. By E. Skudderzik that I have mentioned earlier. Skudderzik. Okay, where he discusses a little bit more. So now n is an integer and it has, the constant has that form. Okay, so now that's one side again taken care of. Okay, so we are dropping equations one after the other through method of separation of variables. So now we'll have to deal with this term and the constant over here. So that equation becomes, next, so I'll write it as next, minus 1 by theta sine theta d by d theta sine theta d by d theta minus 1 by phi sine square theta d2 phi by d phi square is equal to n into n plus 1. Okay, proceeding further, minus 1 by theta, or rather multiplying by sine square theta. So let's say, let's go to the next page. So multiplying by sine square theta, we'll get minus 1 over theta sine theta d by d theta sine theta d by d theta of theta minus 1 over phi d2 phi by d phi square is equal to n into n plus 1 sine square theta. Okay. So now this is now solely a function of phi. Okay. So we will now switch this to this side and this to this side, and what do we get? Minus 1 over theta sine theta. There is something, this sine theta will be on the top here, sine theta. So sine theta d by d theta of sine theta d by d theta of theta minus n into n plus 1 sine square theta is equal to 1 over phi d2 phi by d phi square. So now this is solely a function of theta, this is solely a function of phi. This we will set it up as minus m square again. Okay. So the reasons are very similar. Okay. So I'll just put it very briefly over here. If the m is 0, okay, then phi double dash, let me call it phi double dash, is 0. So that phi becomes equal to a plus b phi, and it starts to grow with phi, okay, which is not allowed. Phi is the azimuthal angle. So as I increase the phi, it grows, it is not allowed. Okay. For one thing, if I start at one point and I come back in the phi direction the same point, the value has to be same, it is physical. Okay. The azimuthal angle repeats. Okay. Azimuthal angle goes and comes back to the same point. So if I apply that principle, then phi starting to phi 2 pi, phi going to 0, starting with 0 and phi going to 2 pi, this value will be different. So it can't be 0. Okay. And similarly, this can't be a positive number. Okay. Then if it is a positive number, then I will get phi is equal to a e to the power m phi plus b e to the power of minus m phi. Okay. And this also blows up with goes to infinity with phi and has no periodicity, with phi. Okay. Because it is the azimuthal angle which goes from 0 to 2 pi. When you come back to the same point after a 2 pi rotation, the value has to be same. Okay. This will not happen over here at phi equal to 0 starting point, phi equal to twice pi ending point, it will not happen. Okay. So that is why negative value is also not allowed. So this side, it has to be a negative real number and m has to be an integer. Okay. We will see why that is the case. So now if we take just this part now, deal with it. So what we have is d2 phi by d phi square plus m square phi equal to 0, and that implies It's just the like the simple harmonic equation. So it's I get phi 1 e to the power I m phi. Because of this plus, I have got an imaginary value over here, plus phi 2 e to the power of minus I m phi. Okay, or it can also be written as phi can also be written as some other phi 3 cos of m phi plus phi of 4 sine of m phi. Okay, so that's one more situation, one more equation taken care of. So here I would like to mention that the choice of m as an integer, what it does is when phi comes back to the same point, let us say phi starts off at 0 and it comes back to the same point, phi is equal to twice pi, then this value acquires the same value, repeats, okay, and that happens only because m is an integer. So m is required to be an integer value, and this is required to be a negative real value, okay, from physical considerations. Okay, so now going to the third equation. So far we have taken care of time and taken care of phi. Okay, so now if we go to the theta equation, what do we have? If we go to the theta equation, what do we have? We have minus 1 by theta sine theta d by d theta of sine theta d by d theta of theta minus n into n plus 1 sine square theta is equal to minus m square. Okay, again we divide by sine square theta and we get 1 by theta sine theta d by d theta sine theta d by d theta of theta plus n into n plus 1 minus m square by sine square theta theta equal to 0. Okay, so now let's just list the equations we have. Okay, let's just list out what we have over here. We have d2t by dt square plus, let me call k square c square as this omega square equal to 0. I'll give this the number 1. Okay, then 1 over r square d by dr r square dr by dr plus k square minus n into n plus 1 by r square into r is equal to 0. That is my number 2. Then I have d2 phi by d phi square, okay, plus m square of phi equal to 0, which is number 3, and 1 by sine theta d by d theta sine theta d by d theta of theta plus n into n plus 1 minus m square by sine square theta of theta equal to 0. This is number 4. Okay. Now we will find a solution to each of these. Okay. So the first is d2t by dt square plus omega square t equal to 0, and then we write t of t as equal to t1 e to the power of I omega t plus t2 e to the power of minus I omega t. Okay, or we write this as t3 cos of omega t plus t4 sin omega t. Okay, which implies that is sum t5 cosine omega t plus a phase. Okay, so this can be found as the real part of sum t tilde, let us say 1 e to the power I omega t, where t1 tilde is a complex number. Okay, so real value applied later. Choice of real is applied later. Okay, that's 1. Then 3, d2 phi by d phi square plus m square phi is equal to 0. Okay, so this again we can write phi of phi as sum phi 1 e to the power of I m phi plus phi 2 e to the power of minus I m phi, or we can write it as phi 3 cos m phi plus phi 4 sin m phi, which is equal to again phi tilde. So this is again equal to sum phi 5 cos of m phi plus an alpha. Okay, so we will write it as sum phi 1 tilde I m phi, and we will take the real later. The fourth equation. Okay, the fourth equation is 1 by sine theta d by d theta sin theta d theta by d theta plus n into n plus 1 minus m square by sine square theta equal to 0. Okay, here we take a change of variable to get this equation into a familiar form. Okay, what is that? Assume eta is cos theta. Okay, there is a slight danger of mixing my n and etas. I will try to keep it separate, so that if this is very long, then that's eta. So d eta is equal to minus sin theta d theta. So that d eta d theta is minus sin theta, or equal to minus square root of 1 minus eta square. Okay. So now d d theta is equal to d by d eta into d eta by d theta, which means it is equal to minus sin theta d by d eta, or minus square root of 1 minus eta square d by d eta. So we are going to apply all these changes, all these substitutions we are going to apply to this equation. Okay. So if we apply, what do we have? We have sin theta, so let me demarcate, 1 over square root of 1 minus eta square, then d d eta. So d d theta is d d eta into d eta d theta. So whatever is inside into d eta d theta, which is minus sin theta, therefore minus square root of 1 minus eta square. Okay. So this d d theta has ended up as d d eta, and so this d d eta and this minus 1 minus eta square outside. So what's inside still we have to deal with. So we have sin theta inside, okay, which is square root of 1 minus eta square, and d theta d eta, and one more minus square root of 1 minus eta square. Okay, plus n into n plus 1 minus m square by 1 minus eta square into theta equal to 0. Okay. So now there is a negative here, there is a negative here and a negative here, that will go. So what we have, and there is a minus, there is a 1 over eta square here that goes with this. Okay. So we have d d eta, and there is a doubling of 1 minus eta square. So I have 1 minus eta square d theta by d eta plus n into n plus 1 minus m square by 1 minus eta square theta equal to 0. Okay. Now a lot of details here, lot of details are required here, which for this course not needed. Okay. And they are presented in Scattersig. So if we accept those details, the solution now to theta in terms of theta, okay, we took a change of variable eta to cos theta. So in terms of theta, if we write, then this is some constant p m n cos theta plus theta 2 q m n cos theta. Okay. So what are these two? What are these, this and that, p and q? So P m n is the Legendre function of the first kind. Okay. And Q m n is the Legendre function of second kind. Okay. Now you can see that we have theta going from, theta is the polar angle, it is going from 0 to pi, okay, 0 to pi all the way, 0 to pi. And so cos theta goes from 0 plus 1 to minus 1, cos theta goes from plus 1 to minus 1. Okay. So this argument goes to plus 1 and goes to minus 1. So now this Qmn, whose argument is cos theta, where theta is ranging from 0 to pi, at plus minus 1 this Qmn blows up, okay. Qmn of plus minus 1 is infinity. So if we have a domain where the poles are included, okay, if we are interested in a domain where theta equal to 0 and theta equal to pi are included, a part of the problem, included in the physics, then Qmn cannot exist, and therefore its coefficient, which is theta 2, goes to 0, must be set to 0. Okay. So initially we will look at such problems only, which means my theta of theta is some constant Pmn of cos theta. Okay. Now we'll deal with this a little later. Let me just mark for now. Okay. So what is now left is the last equation in R. Okay. What is left is the R equation in R. Let me just write it and we'll leave it at that. So I have 1 over R square d by dr R square dr by dr plus k square minus n into n plus 1 by R square into R equal to 0. Okay. The solutions, let me just write it, to this are some constant Jn kr plus R2 yn of kr, if we are presenting them in a standing wave solution, or equal to R3 Hn of 1 kr plus R4 Hn of 2 kr. Okay. And these, so now this is the, so now Jn is the spherical Bessel function, of the first kind, and yn is the spherical Bessel function of the second kind. And hn1 is the spherical Hankel function, of first kind, and hn2 is the spherical Hankel function second kind. Okay, so we'll stop at that and look at these functions further. Thank you.